Hello students, welcome to this session. So in this session, we will move ahead with the discussion on our motor control system. When we perform a voluntary movement, the choice of that movement is not random. It's based on how we perceive the environment, our relationship of the object within it, and the specific goal we want to achieve. And our brain doesn't start from scratch every time. Instead, it draws from a collection of movement plan that we have developed and refined over a lifetime through experience and practice. So, if the exact movement plan for a situation doesn't already exist, the brain chooses the similar plan and modifies it to fit with the current task. For example, if we have learned how to pick a cup of water or cup of tea, we can adapt the same plan slightly modified when picking up a heavier mug or a fragile glass. Once the appropriate plan is selected, the central nervous system customizes it. It determines the correct muscle to activate, the force to apply, and the timing of and sequence of the action needed to achieve the desired outcomes, all based on the situation and the goal we are going to perceive. So this process highlights how voluntary movements is just not just mechanical but highly adaptive and goal driven, shaped by perception, experience and context. Make a voluntary movement. The choice of that particular movement is guided by how we perceive the environment and our relationship to the object within it and the specific goal we want to achieve. So brain doesn't create a brand new or a movement plan every time. Instead, it recollects and draws from the collection of movement plans that we already have developed and refined over the lifetime experience. If the exact plan doesn't exist, the brain selects a similar plan and modifies it to fit the current task. Once the plan is chosen, the central nervous system customizes it, determine the correct muscle and appropriate force, that is the timing of each action to meet the goal. So this customization actually involves close coordination between the frontal lobe, basal ganglia, and the cerebellum, which communicates with each other through the brainstem and thalamus. When the timing of execution, like when it comes to the timing for execution, the pyramidal cell uh, carries the motor commands down through the central nervous system, and these signals reach motor neurons in the brain stem and spinal cord, which then activate the muscle needed for that movement. But motor control doesn't stop at execution. Through adaptation, the body uses sensory input from multiple systems to fine-tune motor plans, correct errors, and even predict the consequences of movements. This adaptation actually allows us to produce constantly effective and efficient skilled action. So we also rely on anticipatory control. So, which means our brain makes postural adjustment in advance for that particular movement. For example, before lifting a heavy object, our muscle adjusts to stabilize the body and minimize any displacement of the center of gravity. And finally, flexibility in the motor control allows us to vary and adjust even simple or complex movement plan depending on the environmental context. So this flexibility makes our movements adaptive, efficient, and well suited for different challenges. So overall, that voluntary movement involves a seamless integration of choice, coordination, execution, adaptation, anticipation, and flexibility, and enabling us to interact effectively with the real world that is around us. The control of voluntary movement. So it follows a clear and structured process. So let's start step by step. So it begins with sensation. So sensory information is gathered from the body and the environment through exteroreceptor and proreceptors. This raw sensory data travels through peripheral afferent neurons to the brainstem, cerebellum, thalamus, and sensory receiving areas of the parietal, occipital, and temporal lobes of the brain. Next, we move to perception, where the brain combines, compares, and filters these sensory inputs. At this stage, information is processed in the brain stem, thalamus, and sensory associated areas, allowing us to make sense of the incoming signals and understand the situation. Once the sensory information has been interpreted, the brain proceeds to the choice of movement plan. So here it uses the perpetual map to select the most appropriate motor plan. So this involves the association area, frontal lobe, and basal ganglia, which help in deciding the goal directed movement. After selecting the movement plan, the next stage is coordination. In this step, the brain determines all the necessary details of the plan, like the required muscle force, timing, tone, direction, and extent of movement for both postural and limb synergies. So the frontal lobe, basal ganglia, cerebellum, and thalamus work together to customize the plan. Following coordination comes execution. So the corticospinal and corticovalar tracts carries motor commands down from the brain to the motor neuron in the brain stem and spinal cord. So these signals activate the appropriate muscles to carry out the movement. And finally, we have adaptation, where brain signal constantly compares the actual movement with the original motor plan, and if there are error, the movement is adjusted in real time, and this relies heavily on spinal neural networks and the cerebellum to fine tune performances. So if we summarize, we can say that the voluntary movement is a continuous loop starting with sensation and perception, moving through planning and coordination, leading to execution, and then adapting based on the feedback. And all of this is made possible by integrate communication between peripheral neurons and the brain stem, cerebellum, basal ganglia, thalamus, and the cortical regions. When we talk about the control of voluntary movement, the cerebellum plays a central role in ensuring that our movements should be smooth, coordinated, and precise. So its primary function are to maintain posture and balance, both when we are at rest and during dynamic tasks like walking, reaching out to some object, or running. In addition, the cerebellum helps coordinate movements not just during their execution, but even before they begin, fine tuning the motor plan for accuracy. To perform these functions, the cerebellum continuously processes a vast amount of information. First, it receives input from the motor area of the cerebral cortex, which provides details about the planned movement. Second, it integrates proprioceptive and kinesthetic information from the muscle and the joints. These signals travel through the dorsal and the ventral spinocerebellar tracts, giving the cerebellum real-time feedback on how the movement is actually being performed. Third, it gathers information from the vestibular system, which helps regulate upright posture and balance, whether we are standing still or moving through space. By combining all these signals, the cerebellum acts like a real-time error correction system, comparing the intended movement with the actual performance and making necessary adjustments to smooth and coordinated and balanced action. Far more than just coordinating the movement, it acts as a comparison center, matching the motor plan signals driven by the cortex and with sensory feedback coming from muscles and joints in periphery. If the actual motor movements does not align with the intended motor plan, the cerebellum make rapid adjustment and adaptations to achieve a smooth and coordinated movement sequence. Movements that we perform repeatedly are stored in the cerebellum as procedural memory traces, which allows them to be executed more efficiently and with less conscious efforts over time. Now, closely linked to maintain attention and awareness during the movement is a reticular activating system known as RAS. So the RAS is a complex network of nerve pathways located in the brainstem reticular formation. It has a critical role in regulating wakefulness, arousal, and attention. The RAS works as a sensory filter. It receives input from multiple sensory systems, visual, auditory, somatosensory, and it prioritizes the most relevant information, suppressing what is unimportant or unwanted. So by doing this, it ensures that only significant sensory signal reach the higher brain centers for conscious processing. So when the RAS is highly active, it promotes a state of wakefulness and alertness, enabling us to focus, maintain posture, and respond effectively to the environment. When its activity decreases, as maybe during sleep, cortical arousal is reduced and we transition into the state of rest. So this system also helps regulate the sleep wake cycle. During the day, the RAS keeps us alert and responsive, while at night, reduced RAS activity promotes sleep. And interestingly, during REM sleep, the RAS activity temporarily increased again, contributing to dreaming and increase the brain activity. The cerebellum also interacts with the RAS to maintain focused attention during motor tasks, and altogether they ensure that we remain conscious, filter out distraction, and maintain the precision over our motor performances. The basal ganglia and its role. So, the basal ganglia are a group of interconnected nuclei located deep within the brain, including the globus pallidus, putamen, and other part of the brain. Actually, together they play a crucial role in motor control, motor learning, and the regulation of voluntary movements. One of the key function is action selection. They help us decide which motor plan or behavior to execute at any given time. This ensures that the movements are purposeful and goal directed. Alongside selecting desired actions, the basal ganglia also suppress unwanted or inappropriate movements, which is critical for preventing involuntary motions. They are also deeply involved in movement intentions, like when we decide to perform an action, such as reaching for an object, the basal ganglia actually help uh, trigger the motor program necessary to carry out that particular movement. In addition, they play a significant role in movement coordination, ensuring that multiple muscle groups work in a precise sequence to produce smooth and efficient motion. And the basal ganglia are also connected to the limbic system, linking them to reward learning, which helps reinforce certain motor behaviors based on their outcomes. Through connections with the superior collicus, they even assist in regulating eye movement and contribute to maintaining posture tone, the overall readiness for movement. So, if we consider an example, reaching and grasping a cup on a table, the prefrontal and parietal cortex first plan the action by estimating the distance and required group. The primary motor cortex signal the basal ganglia with the intention to reach the grasp. The basal ganglia then evaluate the sensory information and select the correct motor plan. Together with the cerebellum, they ensure that the arm and the hand movements are well coordinated and precise. Finally, the motor cortex activates the appropriate muscles, allowing the movement to be executed smoothly without spilling the cup. So, the basal ganglia acts as a, we can say, the key decision making and fine tuning hub for voluntary movements, helping us start, coordinate, and refine motor actions while suppressing any unnecessary or disruptive movements. Control actually relies heavily on how information is processed within the nervous system to produce purposeful and coordinated movements. This involves the continuous interaction between sensory input, motor output, and the central integrative structure of the brain and spinal cord. The processing of information allows us to deal with both the temporal aspects, that is, the timing of the movement, and the spatial components such as the direction and position of the body. Most importantly, this processing also enables us to anticipate movements, allowing a response pattern to the prepared in advance before execution. So there are several ways in which this information is handled. First, we have serial processing. In serial processing, the information flows in a specific sequential order, moving step by step through different processing centers. It's like a strict assembly line. Each stage completes its task before the next one begins. This ensures precision but can be slower because it follows a lockstep progression. Next, there is a parallel processing where the same information can be processed in parallel by multiple centers for multiple activities. For example, when we walk, our brain can process visual input for navigating while also parallelly controlling balance and posture. This makes movement more efficient and adaptable. And the third one, we have a more flexible system called parallel distributed processing. So this combines the advantage of both serial and parallel methods. When a situation demands strict sequential processing, the system can switch to serial mode. When multiple tasks need to happen in parallel, it utilizes parallel pathways. So this adaptability makes it highly efficient for complex motor behavior. So through these different mode of information processing, serial, parallel, and parallel distributed, the nervous system is able to coordinate movement smoothly, adapt or adjust to changing environment, and even prepare responses ahead of time to meet task demands. So the system model of motor control views movements as a result of interaction between multiple neural networks and brain centers that working together. These networks can represent specific regions such as cerebellum and basal ganglia, or they involve smaller interacting neuronal clusters located within a single structure. So, for example, within the basal ganglia itself. So, a classic example of this interaction is seen in the regulation of motor behavior by the basal ganglia through its direct and indirect pathways to cortical areas. The direct pathways, which runs from the putamen to the internal segments of the globus pallidus, has a net inhibitory effect on the motor output. In contrast, um, the indirect pathway, which travels from the putamen through the external segment of the globus pallidum and the subthalamic nucleus, has a net excitatory effect on the internal segment of the globus pallidum. The balance between these two pathways, direct and indirect, is crucial for normal motor control, and when this balance is altered or changed, it can lead to motor dysfunction. For example, um, an abnormally decreased outflow from the basal ganglia, reduced inhibition, and leads to excessive involuntary motor pattern. So, on the other hand, an abnormally increased overflow enhances inhibition and result in um, paucity of movement, where voluntary motions becomes limited or slow, as we see in the conditions like Parkinson disease. So, the systems model highlights how these interconnected networks, especially within the basal ganglia, maintain a delicate equilibrium uh, to produce smooth, purposeful movements. Disruption in this balance is a key factor in many movement disorders. Contemporary landscape of motor control, exciting advancements are shaping how we understand and improve the movement. So one key area is the integration of robotics in the rehabilitation. So robotic assisted devices are being used to provide precise, controlled, and repetitive movements for patients. This targeted therapy not only promotes motor relearning but also enhances recovery outcomes by delivering uh, consistent feedback during rehabilitation sessions. Another area for growing interest in is the human robot interaction. So researchers are studying how humans naturally collaborate and interact with the robot in different tasks. Understanding these dynamics helps in designing robots that can respond intuitively, making them more effective in the assisting movement or rehabilitation. And also, we are learning more about neuroplasticity and motor learning, how the brain reorganizes itself to adapt and recover after injury. So, by harnessing neuroplasticity techniques like non-invasive brain stimulation, and virtual reality-based training are being explored to enhance motor recovery and functional outcome in patients. So, it's a actually very critical topic in motor learning research, like how the transfer of motor skills. So we are investigating how a skill learned in one context can be effectively applied to new tasks or environments, and finding strategies that promote better transfer can speed up skill acquisition and improve motor control across various settings. And another important contemporary issue in motor control is understanding how aging affects the movement. So with age, related changes in motor control, we see gradual alteration in motor integration, muscle in strength, coordination, and balance. So these changes can impact mobility, reaction time, and overall functional independence. Researchers are studying these processes very carefully to develop targeted interventions that maintain or restore motor function in older adults. At the same time, there is a growing focus on active aging and motor performances. So, regular physical activity and exercises programs have been shown to improve strength, flexibility, and coordination. So, by understanding the specific factors that influence motor performance in aging, we can design evidence-based programs to enhance functional mobility, reduce the risk of fall, and ultimately improve the quality of life for old adults. So, in a sense, this area of research is not just about preventing decline, but also about promoting health. Active aging, where individuals can maintain independence and confidence in movement well into their later years of age. Now, a other very fascinating contemporary issue in the motor control is development of brain-computer interface or BCI. So BCI enables direct brain control of external devices such as a robotic, prosthetic, wheelchairs, or computer interfaces. By decoding neural signals, individuals with motor impairment can interact with their environment without relying on traditional muscular movements. So current research is focused on improving the accuracy, reliability, and ease of use of these systems so that it can be more practical and accessible for everyday life. Beyond assisting those with disabilities, BCI are also hold promises for augmenting human abilities. They can enhance motor performance or even restore lost functions. For example, researchers are integrating BIs with exoskeleton and advanced assistive technologies, which can improve mobility, dexterity, and independence for individuals with severe motor impairments. So, actually, the BCIs represents a remarkable step forward, merging human neural command with technology, offering hope for rehabilitation, assistance, and even human enhancement. The other emerging contemporary issue in motor control is use of virtual reality and augmented reality technologies. So VR and AR, it provides immersive environment that allows us to study motor behavior, train motor skills, and assess motor performance in a way that in both realistic and highly controlled. These technologies create safe and adaptable scenarios for rehabilitation, enabling patients to practice movements and tasks that mimic real life situations without the risk associated with the physical movement. So, in research, AR/VR allows precise measurement and manipulation of sensory input, helping us to understand how the brain and body interact during the movement. Whereas in rehabilitation, they provide motivating, engaging, and customizable training sessions, which can accelerate motor learning and recovery for individuals with motor impairments. So, this integration of immersive technology in reshaping the way we approach motor control, offering new possibilities of therapy, skill acquisition, and performance organization. Now, with this, we can conclude our discussion on contemporary issues and theory of motor control learning. So, I hope this session will be helpful for you to understand all these concepts. Thank you for your attention.